Okay, so at this point, we know how to integrate on two-dimensional regions on, say, polygons in the plane, and we also know how to integrate on continuous curves. That's roughly one-dimensional regions in the plane. So now let's talk a little bit about how curves relate to two-dimensional regions. So here is a definition that we're going to use. So let's let gamma be a curve that is a continuous function from a closed interval in R1 to Rp. Say gamma is a closed curve if the two endpoints match up. Gamma of A equals gamma of B. And we want to say that gamma is simple if it never overlaps itself, except we want to allow closed curves to be simple, to count as simple if they never overlap except at the two endpoints. So gamma is simple if gamma is 1-to-1 on the two intervals A to B and A to B. So the only time you're allowed to have 2 points in the interval map to the same point in Rp is if they are the two endpoints. This is a very well-known, very important, and surprisingly hard to prove theorem in topology. This is the Jordan curve theorem. So let's let gamma be a simple closed curve in R2. And then the short version is that the curve has an inside and an outside, but that's state this a little bit more precisely. And let's let capital gamma be its trace. And the conclusion is that R2 minus gamma has two connected components. Both of which are open because gamma is open and in fact compact. And exactly one of the two components is bounded. One is bounded, one is unbounded. And furthermore, both of these connected components have the same boundary, and the boundary is the image of the curve. Sure, this is pretty standard. Here's our simple closed curve. I have to get back to the beginning. And then here is the interior, which is the bounded connected component, and the exterior, which is all this stuff out here. And this is obvious when you look at the picture, but it's hard to prove. And one of the reasons it's hard to prove is that this is not true. In R3. In three-dimensional space, a curve doesn't divide R3 into two components. There's still just one component you can get all around on the curve. And it's also not true if gamma maps into, say, the torus. That is, if your metric space is the surface of a donut, the surface of an inner tube, something like this, and then you can have a curve, simple closed curve gamma that wraps around, and then you'll notice that that isn't dividing the torus into two pieces, the surface of your inner tube, but you cut it there, you still get one piece, one cylinder. So to prove the Jordan curve theorem, you need to somehow use the fact that you're in R2, not R3, and also the fact that you're in R2, not on the torus. So it's actually quite difficult. So we won't prove it, we'll just take it as given. Here's another definition we are going to need. This definition is talking about the fact that this curve, where I go around the circle counterclockwise, is not really the same curve as this curve where I go around the circle clockwise. In particular, when you deal with line integrals, when you have a tangent vector that points in some direction, you're going to get very different line integrals for the clockwise curve and the counterclockwise curve. So we're going to talk about what we mean by a counterclockwise curve, what we'll call a positively oriented curve. So we're going to define this for C1 simple closed curves. It's C1, meaning it's continuously differentiable, and it is also a simple closed curve. And let's suppose the following. So the idea is your tangent vector, there are two vectors perpendicular to it, what we can think of as normal vectors. And there's the one on the left and the one on the right. And we say a curve is positively oriented, is C1 oriented, if the normal curve on the left is the one that points to the interior of the region, to the bounded region promised us by the Jordan curve theorem. Let's let omega be the bounded region promised to us by the Jordan curve theorem. You can see that that just means omega in R2 is open, bounded, and the boundary of omega is the image of gamma. The Jordan curve theorem promises us that such a set must exist, and it's not too hard to convince yourself that there can't be more than one set like that. Then gamma is 1-to-1, at least on open at least except at the endpoints. So that means its derivative can't be zero everywhere. If derivative was zero everywhere, mean value theorem, it would be constant. And then it's certainly not at 1 to 1. So if t is in AB and gamma prime of t is not equal to 0, recall the tangent vector at the point gamma of t is gamma prime of t divided by the norm of gamma prime of t. It's the vector of length 1 in the direction of gamma prime. And I suppose there is one technicality. The two endpoints come from A and B. So if it's one of the endpoints, we're going to require that then the normal vector n of t, we're going to define it this way. N of t is, you take gamma prime of t, that's a vector, you rotate it 90 degrees in the counterclockwise direction. You can do that by multiplying by this matrix. It's not too hard to check that this matrix just rotates the vector and in particular doesn't change its length. So if we divide by the norm of gamma prime of t, we will get a unit vector. And that's how we define our normal vector. And then we say that if the normal vector points into omega, then we say gamma is positively oriented. What do we mean by points into omega? If for every point where we have a normal vector, that is, every point where gamma is not just stopping for a minute, we have that a small constant times the normal vector has to stay in omega. Then we say gamma is positively oriented. So this region, for example, this curve is positively oriented because if you draw the tangent vector, you rotate it 90 degrees counterclockwise, it always points a little bit into the region, not out of it. To point out, you have to rotate clockwise. Here's one other definition I would like to state. So we say that a curve, specifically it has to be a C1 curve, we call it regular if gamma prime of t is not equal to 0 for all t in the domain. And that would completely disallow any sort of corners. Because at a corner, either the derivative doesn't exist or the derivative exists. We can make it the derivative exist as a corner, but it's got to be 0. Now, I want to be able to do analysis to do integration on things that do have corners, on polygons. I like polygons. So I want to allow myself to have some corners. I want to allow myself to have finitely many corners. And I'm going to do this a little bit differently from how your book does it. Your book lets your derivative just stop existing at certain points. I'm going to insist that your derivative has to exist at all points, but it's allowed to be 0. One other piece of weirdness I want to disallow, that's why I wrote an and there. I want to disallow something like a spiral point. So gamma of t is something like t cosine 1 over t, t sine 1 over t. So it spins around infinitely many times before it gets to the target point. Int gamma of 0 equals 0, 0. I don't want to have something like that, or a sine wave that wiggles around infinitely many points. This would be something that looks sort of like this. You oscillate back and forth infinitely many times. I don't want to allow I don't want to allow bad points like this either. So I've said that gamma prime of t has to be non-zero for all but finitely many t, and at the points where it is 0, I'm going at the points where gamma prime is 0, that is the finitely many points where the tangent vector doesn't exist. I'm going to say that the tangent vector has to approach a limit from the two sides, and that will be enough to allow, and that will allow us to have these kinds of corners where the tangent vector is heading towards this from this side and this from that side. But it will disallow something like this where the tangent vector, something like these spirals where the tangent vector just spins around and around and around and around infinitely many times, or the sine wave where the tangent vector flips up and down, back and forth infinitely many times. the usual annoying caveats at the endpoints. And so that is what I mean by a regular curve. Here's a quick lemma that I want to state about piecewise regular curves. So we take a piecewise regular curve, and let's let P be the set of points where gamma is 0. There's only finitely many of them. We'll go ahead and throw in the endpoints just as because why not? And then we can put them in order. There's finitely many of them. And then if T is not in P, then gamma prime of T is not 0. And let's let gamma J be the curve gamma, and then you restrict it to the interval up to Tj. And then this is fairly straightforward to show. If f is a continuous function defined near the image of gamma, then the integral of f over gamma, which remember we can define just in terms of the arc length parameterization, and it doesn't depend on your choice of parameterization. It turns out that it's just the sum of the integrals over the gamma j's over the pieces. And you can also write this as the integral from a to b f of gamma of t and times gamma prime of t, its modulus dt. And we proved that the left-hand endpoint and the right-hand endpoint, the left-hand term here, the right-hand term over here, we proved those were equal by back in lecture 8.1.1. So this is from lecture 8.1, sorry, section 8.1. Lecture 1, part 3. Relating those two is a proposition from there, and then to get the piece in the middle, we just throw in proposition 3.1.6. All right, that sort of just orientation. The interesting part of this lemma is about integrating vector valued functions. Let f be a vector valued function going from v to rp. And then we can't really write the integral of f dotted with the tangent vector on all of gamma because the tangent vector doesn't exist at these finitely many points. But if we look at one of the gamma j's, then we can at least meaningfully tweak the definition of T, let's call it Tj, just to be as just the limits. So these meaningfully exist. F is continuous. The tangent vector now is continuous. So we can sum these from j equals 1 to n. This is the integral from a to b, f of gamma of t dot product with gamma prime of t dt. And the right-hand side, the integral on the right or the sum on the left does not depend on the parameterization. If you reparameterize gamma, and eta is piecewise regular, then we must have that f of gamma of t dot with gamma prime of t dt is equal to the corresponding integral with etas. Suppose eta needs a domain. As I said, you cannot really define, you can't really say that the integral of f dot to t ds exists, because t doesn't exist everywhere, but we're going to wiggle out that. We'll just say that a piecewise regular function, then at a piecewise regular function, the integral of f dotted with the tangent vector is just what you get by breaking it up into pieces or by writing it as an integral, and that doesn't depend on your parameterization. So we are finally in a position where I can state Green's theorem, and everything I write down will be something whose definition you know. So I'm going to state Green's theorem in its most general form. Will not prove it in this full generality because we've got only about 1 1/3 lectures left in this semester, but we'll prove a bunch of important special cases, and it is true in this case. So let's start with a bunch of piecewise regular curves. And let's say that their domains are all 0, 1. You can always reparameterize this. So it's true, be piecewise regular. positively oriented simple closed curves. And let's let omega k be bounded. And be the interior of each gamma k. That's the connected open and set whose boundary is the image of the curve. And we're going to suppose we're going to be dealing with a domain that's one of these Jordan regions. And in Green's theorem in general, you're allowed to delete some holes if you want to. So we're going to let omega naught be the big region and the omega k's be little holes, and we're going to say that they have to be disjoint holes. So X is a closed set, and we're maybe throwing away these open holes inside. And now let's let U be open. X a subset of U, and F goes from U to R2, be continuously differentiable, C1. And the conclusion of Green's theorem is that if you integrate over the region X, this quantity, partial F2, F is a vector. It's got two components. I'm calling them x1 and f1 and x2. You integrate partial f2 with respect to the first coordinate, which I'm calling x1 instead of just x in this case. Because I think it sheds some light on the problem. That is equal to the integral over the boundary of f dotted with t ds, where the integral over the boundary of f dot t ds, that's the integral over the outer boundary, minus the integrals over all the inner boundaries. And where f1 and f2 are continuously differentiable, so the thing you're integrating over x is continuous. So I'm claiming that this quantity is Fubini integrable in the sense we've seen. Of course, you really want this theorem in terms of Riemann or Lebesgue integrals, but since we don't have time to go into the details of Lebesgue integration, we're going to just state Green's theorem for Fubini integration. Draw you the picture. Here is our gamma naught, it's positively oriented. Here are little holes, gamma 1, gamma 2, gamma 3. Then we're integrating over this region inside, but not the gaps. And we're saying that F has to be defined in some little neighborhood of our domain. Maybe it's not defined in the inside here, but it does have to be defined near the boundary. And then when we subtract off the integrals over these little boundary regions, that's really the same as adding the integrals if we oriented them in the other direction, which might be more consistent. Now, the first special case I want to talk about is polygons. Remember, we said that polygons were closed and bounded, but I'm going to go ahead and write out that we want them to be bounded anyway. And the conclusion then is that Green's theorem is true. In P. So this is going to be the reverse of homework 31. In homework 31, I proved in the video lecture that you could integrate continuous functions, that they're Fubini integrable in triangles, and then for your homework you put it together to show that you could integrate continuous functions in arbitrary polygons. And for the reverse, I am going to ask you on your homework to prove that Green's theorem is true in triangles, and then I'll show you in the video how to put the triangles together. So let's let T be a triangle. In the interest of making your life easier, I'm going to say that one of the three sides of the triangle has to be vertical. Talking about triangles that look like this, perhaps like this. And then by your homework for this lecture, you'll prove that Green's theorem is true in T. And now if we take an arbitrary polygon, it is the union of such triangles. So what you do is you draw a nice straight vertical line through every vertex. Occasionally they'll overlap if you have vertices that are stacked on top of each other horizontally. And then that splits your polygon up into these nice vertical strips. And if your vertical strip happens to be, and then the pieces inside the vertical strips, so a piece like this, its boundary can only be either a part of the vertical strip, can only be vertical lines, and then it has to be cut off on the edges. It has to be cut off by lines connecting the two sides, so you must end up with a trapezoid. And I don't want to integrate over trapezoids because your homework is triangles, but fortunately you can always cut a trapezoid in half and get two triangles. So we've got a bunch of half trapezoids, or maybe the piece inside the strip is just a triangle. That works too. But at the end of the day, what we've done is we've split our polygon into a bunch of triangles like the kind you see on your homework, and you can always do that with a polygon. Then the conclusion of what I just wrote, the picture I just drew, we can summarize that as we may write P as the union of n triangles, of finitely many triangles, where what's true about the TKs? Each TK is a triangle with a vertical side. And if you've got two triangles that intersect each other, well, either they're in separate strips, and the only place they can possibly intersect is on their boundary, or they are two triangles within the same strip, and then again they can only intersect along their boundary. I didn't draw it on this polygon, but if you had another or a bit of a triangle as part of your map, then that would intersect another triangle. You could possibly have it intersect it only at a corner, but in any case, triangles only intersect other triangles on their boundary. So we see that if you pick two distinct triangles, then their intersection of the two triangles, it's equal to the intersection of the boundaries of the two triangles. And that is either empty or it's one point or it's a line segment, because that's the only way two triangles can intersect it. If they're intersecting on the boundary, either it's a line segment or just one point or nothing. So now let's talk about putting this together. Let's define P sub j as the union of the first j triangles. And then by your homework, Green's theorem holds in P1, which is just the triangle T1. And so we just need to do an induction argument. We need to show if you start with a polygon and put it together with a triangle, and you've got Green's theorem in the polygon and triangle, then you've got it in their union. So I will state the lemma. You should think about why it's enough to give you Green's theorem in a polygon, and then at the start of the next video, I'll prove the lemma. If I've got two polygons, let me call them T and Q. And Green's theorem holds in each of them. Then Green's theorem holds. In their union. And that's the first thing we'll prove in the next video.